Okay, everybody, it's time to get started. Welcome back, and this is our last regular class. We're going to do a little bit of new stuff today, and then next time we will just be talking about kind of review topics for the final exam. We do have our last homework assignment due today. I hope you've had a chance to check it out. And a little announcement. You probably already know this if you need to know this, but I am doing a review session tonight for the comprehensive exam, the linear algebra section, at 5 p.m. So if you are a senior, you should probably come at this very same Zoom link. It'll be great. Anyway, I think we can just get right down to business for our last day. Are there any questions at this point about the final exam or anything? I don't think there's anything I need to say about it right now. It's going to be like our other exams.
I had a question actually about the review session.
Yeah, sure.
Record it.
Yes, I am going to record it, and I will. I'll put it on YouTube, and I'll send the address to somebody who can forward it to all the seniors.
Okay, awesome. Thank you.
I guess you're not coming then, huh? That's all right. Be sure to like and subscribe. Okay, let's try to finish up what I was talking about last time. I left you with the very strange observation or idea. I didn't really give much justification for this at the time, but that's what I want to talk about today. Rearranging a series. Do you remember what I was talking about last time? Rearranging a series can change the value. It's a true fact. The example I used last time was this, minus 1 to the n over n. Now this one, when you do this series, this is negative 1 plus a half, minus a third, plus a fourth, minus a fifth, plus, etc. In this order, it adds up to negative ln of 2. But it is possible to add it up in a different order, and we saw, I showed last time a particular reordering of this to make it add up to, so another order made it add to 3/2 times negative ln of 2. All right. I don't want to go through the details of that again, but it is a true fact and a very strange fact in my opinion. This is actually one of my favorite theorems from elementary real analysis. Is that sometimes if you rearrange the terms of a series, you can get a different answer. And what I want to talk about today is under what conditions can you do that? Like for which series is it possible to rearrange and get a different answer? And then also I want to talk about what can the answer be? When you rearrange it, what are the possibilities for what you could turn the answer into by changing the order around, all right? This is so weird, of course, because ordinarily, addition has the commutative property. That means you can change the order around when you're adding things, and you'll get the same answer. It turns out that is not true when you're doing an infinite sum of things. So in an infinite series, those terms are not fully commutative. You can't rearrange. Them all and expect to get the same answer. Okay. Anyway. All of this has to do with a simple concept that we haven't talked about yet, but I will tell you about it. So all of this, it has a lot to do with looking at the series. The series AK versus the series of the absolute value of AK. All right. So obviously we all know that the absolute value AK is larger than just AK, right? So when I take the absolute value of a series, we expect that it will be bigger, right? So we expect that the sum absolute value AK is larger, greater or equal. Obviously, if they're all positive to begin with, you get the same thing again. But it's like this, right? When I sum the absolute values, got my little beverage here. When I sum the absolute values, it's bigger than the original series, okay? And so it's possible for the sum of AK to converge, but the sum of the absolute value AK diverges. At least that should seem possible to you, because when you take the absolute values, it makes the whole thing bigger. And it may be, and in fact it is true sometimes, that the original series can converge, but when you take the absolute values, it gets bigger, and in fact gets so much bigger that it diverges, like it becomes infinite. All right? And in fact, this exact situation happens in that example that I was discussing last time. So remember last time we talked about the fact that the sum of 1 over n, this is called the harmonic series, and it diverges. Like these things, when you add them up, it sort of adds up to infinity, right? But this, with an alternating sign, this converges, right? You get minus ln of 2. And so this is an example, actually, where this thing does converge. So this one, with the signs, this converges. But when you take the absolute values every time, this, of course, equals just 1 over n. Taking the absolute values, all it does is, in this one, is just turn some of those minuses, turns them all to pluses. All right, and this diverges, right? So this is an example of what I was talking about, where sometimes the original sequence converges, but once you take absolute values, it ends up diverging. All right, it can happen, and there's simple terminology for all of this. So here's an easy definition. If this is a series and the sum of the absolute value converges, we say that AK, the series AK, is absolutely convergent. Absolutely convergent. It means that not only the series converges, but even when you take the absolute values, it still converges. All right, which is like stronger than just saying that it converges, because when you take the absolute values, in theory, everything gets bigger, which means it might not converge anymore. But if it still does converge, then it's called absolutely convergence. And if not, so the other situation, which is a little more delicate, which is the situation of this example that I was saying, if this one converges, but the absolute values diverges, then we say that the sum AK is conditionally convergent. Conditionally meaning it does converge, it is convergent, but only when you leave the signs like they are. If you were to change all the signs to positive, then it diverges. All right, so that's what conditionally convergent. It converges, but only as written, and you need the signs to stay like they are. If you make them all positive, it diverges. All right, and this business about rearranging, all the questions that I was asking before can be answered in terms of absolute convergence and conditional convergence. So I have two basic sort of big theorems, I guess, although we don't have time to do the real proofs of these. So I'm just going to try and give you an idea about these two big sort of answers. The first question I asked was, under what conditions can you get different answers by rearranging the terms? And the first big statement, number one, is to answer that question. It says, if AK, the series AK, is absolutely convergent, that means it converges even when you take absolute values, then every rearrangement has the same value. So if it's absolutely convergent, that means it converges even if you take absolute values of every term. Then, however you rearrange, you get the same answer. So rearranging the terms does not change the value. Every rearrangement has the same value. What about if it is not absolutely, but if it is conditionally convergent? That means the original thing converges, but the absolute value diverges. So this is statement number 2. If some, oh, it's a terrible summation, some AK is conditionally convergent, then in this case you can get different answers by rearranging the terms. And in fact, this is my favorite part. This to me is the most surprising of all of these things. Then, well, let me say first of all, then some rearrangements can have different values, which in itself is surprising. Can have different values. And the other question I had asked is, what kind of values can you get by rearranging? And the answer is all of them. So what I'm going to say here is, and every real number can be achieved by some rearrangement. So what this means is, not only can you get different answers sometimes by rearranging it, but you can rearrange it to add up to any number you want. So you can make it add up to 0. You can make it add up to pi over 2, whatever. Any number you can, any real number can be achieved as the value of the series under some rearrangement. So these are the two things that I want to discuss in our remaining 35 minutes or so, and I think we can do this. Like I said, I'm not going to do very detailed proofs for either part here. All right. Let's talk about the first one first. If it's absolutely convergent, then every rearrangement has the same value. I want to try to see if I can convince you of that. So first off, number one, I'm going to say let AK converge. So this is absolutely convergent, right? I put the absolute values in there. So this is absolutely convergent. Then that means that the thing without absolute values converges, and every rearrangement has the same value. That's what I want to demonstrate. Or I'm not going to do the proof like I said, but I'm going to try and give you an idea of why it's true. And what the absolute convergence has to do with anything. Why should the absolute convergence matter when it comes to rearranging the series, all right? If it's absolutely convergent, then I want to demonstrate that the original series converges and every rearrangement has the same value. Okay, so here's sort of, not really a proof, but this is the idea of the proof, all right? I'm going to say let the sum AK be some specific number A, and I'm going to let this RK be a rearrangement. So what that means is the sequence RK consists of the same numbers in the sequence AK, but they just appear in a different order. All right. This is a little complicated if you think about the fact that AK can repeat some values. Any repetitions of values from AK, they occur. Those same repetitions occur in RK. They just occur in a different order. All right. So let Rk be some rearrangement, and then we want to show that the series Rk also equals A. All right. Of course, we're assuming that it's absolutely convergent, right? That's the key assumption that makes all of this true, that the series is also converging when you put absolute values. Okay, let Rk be a rearrangement, and we want to show that Rk also converges to the same value, and somehow this is going to involve absolute value, taking absolute values of the individual terms. All right, how do we make this work? Of course, all of these series which converge, they have to do, really what we're talking about are the sequence of partial sums. So I'm going to say let Sk be the partial sums of the A's, and Tk be the partial sums of the R's. Remember, the R's are the same as the A's, they just come in a different order, right? That doesn't mean the S's are the same as the T's, and they're different sequences, but they're related, I guess. Anyway, what I want to show is that Tk approaches the big A, right? We're supposed to show that the series of the R's equals A. The series of the R's is the same as saying the limit of the partial sums of the R's, which is the Tk. All right, and the idea is we do some sort of epsilon over 2 thing, trick, thing, whatever. You know, you want to show that Tk minus Tk approaches A, you need this to be small, right? But the way you do this, if you wanted to do the full proof, you would say this, I'm going to break this into 2 bits by adding and subtracting Sk. So Sk, remember, is the partial sums of the original thing before you rearrange it. And we can say Sk minus A. This can be very small, since we have already assumed that Sk approaches A, right? A is the value of the original series, and Sk is the sequence of the partial sums. So this part, Sk minus A, you can easily make that this is going to be less than epsilon over 2. That's the easy part of the proof. The hard part is this, and this is where I'm going to get a little vague. How do you be sure that Tn minus Sk is also going to be as small as you want, like less than epsilon over 2? That's what you need it to be. You have to think about what this looks like. Tn and S, why did I put K's? I meant N here, or maybe I meant K everywhere. I'm always saying, I meant to say K's. You can call them whatever you want. You should be consistent though. N's or K's, whatever. Tk minus Sk, what does that look like? So Tk minus Sk, can I just say this has lots of cancellation. When you subtract, because Tk looks like R1 plus blah, 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 plus Rk, and then you're subtracting A1 plus blah, 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 plus Ak, right? That's what Tk minus Sk looks like. And the R's and the A's, they are the same, but in a different order. Now, that does not necessarily mean that they will actually fully cancel here, because it could be that, like this is the first K terms in the sequence. Now, once you rearrange them, maybe not all of these K are the same as the first K terms in the rearranged version, because maybe you swapped out some of the early ones and you push them way later in the list, and so they no longer occur in here. But when the K is big enough, most of these are the same and will cancel out. In fact, we can choose the K to be large enough to make the first, 100 of these cancel, or the first 1,000 of these cancel. And this is the delicate part of the proof, which I'm going to skip. So this, let me just say sort of vaguely here, when K is very large, the ones which don't cancel from here must be very, very large. We can choose the k. I mean, their subscripts must be very, very large. They must be very deep into the sequence, and so we can choose this k so big that the first block of all of these terms will cancel, and then what that means is you can break this down into what remains from. What remains from here will be less than or equal to just sort of the ones which end up not canceling, which I'll call them maybe an1 plus an m. You don't know what the little numbers are, but these ones are all deep in the sequence. So all of these are far down in the sequence. And then you can do this. And this will be less than epsilon over 2 since it's absolutely convergent. This is where you use the absolute convergence. If it's absolutely convergent, it means that when you add together the absolute values of the terms that are far down in the sequence, they're all very small. They're basically like 0, all of them. All right. That says epsilon over 2. All right. I'm trying to give you the vague idea of why this is true. I hope that what I've said means something, although it's not. It doesn't constitute a real proof. But I'm trying to give you an idea of where the absolute convergence comes in. If it's not absolutely convergent, then you can still do this, but there's no guarantee that these numbers are going to be small. But if it is absolutely convergent, it means that eventually these absolute values that you're adding together will all be super, super tiny. All right. Any thoughts about that? All right. This was the first fact. In my opinion, the second fact is more interesting and actually much easier to see. So this of what I wanted to talk about today. This is sort of the hard part. Remember, I wanted to talk about these two big facts. I just said the first one. If the sum is absolutely convergent, then every rearrangement ends up having the same value. You rearrange the terms. It's because you rearrange the terms. The difference between the original and the rearranged one, if you were to like subtract them, almost everything would cancel out except for the terms way at the end, and those are so small that they're basically going to be 0 anyway. What about this though? If it's conditionally convergent, then different rearrangements can have different values, and every real number can be achieved by some rearrangement. It means, for example, that series that we talked about yesterday, which added up to the natural log of 2, it means that it is possible to rearrange those terms so that instead of natural log of 2, they add up to 0, or they add up to 1, or whatever you want. You can rearrange it and make it happen. Let's see how that works. Actually, this one, I don't know if you felt like you got kind of lost with the first one. I guarantee you will understand the second one. It's quite a bit simpler. I'll do it over here. So this is number 2, part 2. This is my favorite part. So for part 2, I say if this AK is conditionally convergent, that means that AK converges, but when you take the absolute values, it does not converge. Then we can rearrange to achieve any value. All right. Rather than trying to do this in generality, can we just try and do this with the example, the specific example I was talking about yesterday? So let's try it with this particular example. This is called the alternating harmonic series. Sum n equal 1 to infinity of minus 1 to the n over n. All right? It looks like this. Minus 1 plus a half, minus a third, plus a fourth, etc. Okay? And as we saw yesterday, this, in this order, it adds up to this, minus ln of 2. We didn't actually prove that, but using my Excel spreadsheet, you can see fairly fairly clearly that the values, they do add up to something. They converge to something, and it turns out it's the natural log of 2. I would like, here's my little goal for the end here. Let's try to rearrange it so that it adds up to 0. All right, it's not so difficult. Check it out. First, a little observation here. Observe. What if we consider this series, but only take the positive values? I'm gonna like try and sort of separate it out. What if I only look at the positives? If we sum only the positives, the positives are the even ones, right? So actually it looks like this is what you get when you sum only the positives. Can anybody say, does this converge or not? Or maybe any suggestions about how we could try and like simplify this or somehow to compute this series? What does it add up to? Or if you can't tell me what it adds up to, can you simplify anything? Take the half out. Yeah, that's a constant multiple on the inside, can always be factored out of a series. So this is the same as 1/2 sum 1 over n. Right? And what can you say about that series there? This actually is the harmonic series, which we discussed yesterday, which diverges. So this here, that part right there, this diverges. Can I just say like to infinity? Actually, these things, it means if we take only the positives, they will eventually add up sort of out to infinity, right? All the positive ones, they will add up as high as you like, diverging. Okay, what about the negative ones? If we sum only the negative ones, well, the negatives are the odd ones, right? They look like this. They're negative, but they are the ones which have odd denominators. And this, now it's not so easy to factor the 2 out of this, but if you allow some inequalities, that's less than or equal to minus 1 over 2n. Right, I made the denominator bigger, which makes the fraction bigger, but it's negative, and so it becomes more negative. Is that right? It becomes less negative. I made the denominator bigger, makes the fraction... What? I'm confusing myself with the denominators. Yeah, I think this is right. Anyway, this diverges also. That's what I'm trying to say. You can factor this out. This also diverges, but this time like to minus infinity, right? If you take just the positives, they kind of add up to infinity. If you take just the negatives, they kind of add up to negative infinity. Actually, this is true for any conditionally convergent series. This is not a special property of this series in particular. But if the absolute values diverge, that means if the absolute values diverge but the original series converges, it means that the positives and the negatives taken separately must both diverge to infinity. Sort of the positives will add up to infinity, the negatives will add up to negative infinity. This will always happen. So this is true in our particular example, but it is actually generally true for any conditionally convergent series. What it means is when we, so I would say when we sum the positives, I'm just saying this informally, positives we get infinity. When we sum the negatives, we get negative infinity, right? That's what I just said. This is sort of the informal version of that. All right then, are you ready? How can we rearrange things so that it adds up to 0? So let's rearrange the series to sum to 0. Here's my strategy. I'm just going to pull the first term here, which is -1. I keep that one first. I'm going to try to write down for you specifically what the order is that makes it add up to 0. So you take negative values, negative terms, until the sum is below 0. And so in our example, we just take the first negative term, and it's -1. And so the sum so far will just be -1, which is below 0. And then we take positive terms until the sum is above 0. So I take -1 first, and then I take 1/2 and 1/4. Well, I'm adding these into the sum, so I'll write it this way. 1/2 plus 1/4 plus 1/6 plus 1/8. So I did a little calculating on my own when I was putting these numbers together. It turns out if you add these up, 1/2 plus 1/4 plus 1/6, 1/8, now the sum is now 0.0416, etc. See, when you start with -1, which is negative, and then I'm just saying you keep on adding enough of these positive terms until eventually the thing goes above 0, all right? And this is how many it takes. So when you add only to 1/6, it's still going to be negative, but if you add another 1/8, then the sum becomes positive, all right? Then I take one more negative term, another negative, which in this case is the next negative term was 1/3, right? You have to sort of keep track of the positives and the negatives as two separate lists, and you're kind of like interleaving them in some way. You take another negative, and once you add that on, the sum now is, I did this on my calculator, 0.2916. All right. This used to be the sum, but then I added, or I subtracted a third, and the sum drops down to be this. But now I can just pull positives again and add them onto it until this, again, goes above 0. So now I take positive terms again. In this example, so I worked this out, the next, you gotta start where you left off, because I have to rearrange them. I can't take, say, the 1/2 again. So you take 1/10 plus a 12th. It turns out you gotta go up to 1/16. But at this point, the sum is now 0.0255. All right. I'm pulling these numbers so that it always kind of hovers around 0, right? I add a bunch of positives until it just goes above 0. Then I add a negative, drops back down. Then I add a bunch of positives until it just goes above 0. Then I add a negative, it drops back down. And then you just continue doing this. All right? With an exclamation. Okay? You should ask yourself, like, can you even do that? Like, I say you keep on adding positive until it goes above 0. Maybe there aren't enough positives to make it go above 0, but actually there are, because we said already that if we were to add up the positive terms, I said up here, if we sum the positives, we get infinity. So you can always add more positives to make it go up above some particular level. And similarly, you could do that with negatives if you wanted to. All right. So actually, I did this on my handy dandy Excel notebook. Check it out. I would like to show you one more time. Come on. Sorry, this is going to be great. Here we go. Here we go. Okay. So what you see now is the same Excel sheet from yesterday. This is the one where I just take the ends in order. So down here, see, just 1, 2, 3, 4, 5, the standard ordering. And I have the AN and the SN. And if you go down far enough, eventually, Remember this from yesterday? I made my little chart here. Here's the values. You can see they bounce back and forth, but they do converge to some value in there, which turns out to be the natural log of 2. All right, check it out. I'm going to my next tab. What you see here is the pattern that I was just writing on my scribbler screen. What you see is the first term there is the 1, which makes the sum be -1. And then I added 4 evens, and you can see the sum every time gets slightly less negative until I add the 8th, in which case the sum is now positive. And then I add another negative, another odd number, which makes it negative again. And then I add 4 more positives until it becomes positive again. And then I add another odd, which makes it negative. And you can see this if I continue. So I continued this quite a while. And check it out. I made the same chart. And here you can see these values. I don't think you can see my my mouse here, but you will see this time what you should see is, if you just look at these dots, like starting from the left, you will see they begin at -1, and then they sort of slowly go up until there's 1 which is above 0, and then it dumps back down, and then it slowly goes up again until there's 1 above 0, and dumps back down, and so on. And if you continue this long enough, it will converge to 0. All right? This is a rearrangement which converges to 0. The rearrangement consists basically of delaying the odds, right? The evens, you can see I color-coded them. The evens come very often, but the odds are sort of coming only every 4th thing. We take one of the odds. This is strange rearrangement, but it is a rearrangement. Every term will eventually occur in this list. All right. Oh, it looks like I messed it up right here. You can see only 3 evens there. Okay. Any thoughts about that? Check it out. I'm going to go to the next tab here. This one, I made it add up to 1. So in this case, I start again with the first one, which makes the sum -1, and then I'm going to take positives here, even terms, keep going until the sum goes above 1, which happens after term 62. It finally goes above a 1, and then I take one more odd term. It dumps down below 1, and then I add slowly, adding the evens until the sum goes past 1. It doesn't happen until here, term 120. All right. This one, if you look at the graph, you'll see same kind of thing. Only you have to add a lot more dots before you go past. You can see there they are converging to 1, right? Every time you add enough positives until it goes just beyond the 1. And then you add a negative, and it goes way down, and you have to add a bunch of positives until it goes past the 1, then you add a negative, and so on. But anyway, this will be a rearrangement which adds up to the number 1. And like I said, you can do this for any number. There's nothing special about zeros and ones here. It's you can make it add up to anything you want. All right. Any thoughts about that? Any questions? This to me is a very interesting fact, and I like it. All right. Well, I think that'll do it then. We got 10 more minutes on the clock, but I don't have anything else to tell you. I've told you everything there is. No, it's not everything there is, but that's all that I care to talk about. So come back on Friday, and we will talk about the test. I'll make up some kind of a review sheet, and maybe we can just we can talk about things like all together if you like, or we can split up into groups and just try and go over, problems on the review sheet, whatever you guys want to do. All right. I think that'll do it then. I will see. Maybe I'll see some of you at 5 o'clock for the linear algebra. Otherwise, I'll see you on Friday.